Hello and welcome to Science Spotlight. Today we're hearing from Bella Pfeiffer, an automation research associate at Covaris. Bella will be discussing a persistent challenge in genomics, why FFPE samples struggle in whole genome sequencing. She'll reveal how a unified AFA-based workflow can overcome these obstacles to deliver high-confidence data. Hi Bella, it's great to meet you. Thanks for joining us today.
Hi, how are you?
Yeah, good, thank you. So to start with, I was wondering if you could tell us a bit about yourself and the work you do.
Yeah, absolutely. So my name is Bella Pfeiffer. I work here at Covaris as an automation research associate. I'm in our solutions department, and I do a lot of our work with automating our assays on liquid handlers. I also do some of our bioinformatic pipelines, just anything related to automation. I have a bioinformatics master's from Boston University and a degree in biology from George Washington University. I worked previously at Harvard and a couple other startups. So yeah, really excited to be speaking today.
Lovely, thank you. So looking forward to hearing a bit more about your work.
Awesome. Thank you again for having me. Today we're going to be walking you through how we can enhance our extraction and whole genome sequencing library prep from FFPE samples. So today I'll be walking you through our work, which was previously presented at the 2025 conference for the Association for Molecular Pathology here in Boston. We'll start with some background on FFPE, NGS workflows, discuss the key challenges we face with this sample type, then show you how Covaris' solution can help. If you'd like to dive deeper into the details after this presentation, you can find our full poster and additional resources on our website at covaris.com. Let's start by understanding what FFPE samples are and why they're so challenging to work with. The abbreviation FFPE stands for formalin-fixed paraffin-embedded tissues, which means these samples have been preserved in formalin and then later embedded in paraffin wax. This is a very standard method of sample preservation, particularly for tumorous samples, and it's been used for decades. The vast majority of historical clinical samples are preserved as FFPE samples, which makes them an invaluable resource for cancer diagnostic and research efforts. However, the formalin fixation process creates pretty significant challenges for genomic analysis later down the road due to issues with fragmentation and nucleic acid modification. The major steps of any FFPE workflow fall into two categories: extraction, or the removal of DNA from FFPE samples, and library prep, preparation of DNA for whole genome sequencing. Both sections create their own challenges. During extraction, we face signal loss, as though frequency variant molecules get permanently lost via inefficient extraction. We can also see contaminants and inhibitors in extraction that interfere with downstream reactions, skew quantification, and reduce efficiency. At the library prep stage, we often see that low fidelity prep creates artificial variants that can mask real signals, or they can be indistinguishable from true mutations. And most critically, we can see irreversible sample loss if a library fails to deliver enough yield from a very scarce sample. The growing demand for genomic data from FFP samples requires a better method. Current workflows are a barrier to reliable, scalable science. What we really need to ensure the best genomic data from FFPE samples is a single automated workflow that de-risks every step from sample to variant calling that can deliver maximum sensitivity, accuracy, and operational efficiency. So how do we address all of this? Let me show you the Covaris solution. So here's a brief overview and introduction to our TrueExtract plus TrueCover workflow, which is the Covaris solution to FFPE extraction and library prep. We'll be covering the highlights of this workflow here and expanding with further analysis as we dive into the data. It's important to note that this full workflow can be completed in only 2 days, and it contains all the steps necessary to go from FFPE tissue all the way through to sequencing analysis. This is a notable advantage over other costly, time-intensive workflows from other suppliers. Day 1 is our TrueExtract extraction. We start with deparaffinization and tissue rehydration, then use AFA-enhanced paraffin removal and tissue homogenization, followed by centrifugation to separate out the DNA. While this kit performs total nucleic acid extraction, we will be focusing exclusively on DNA analysis for the remainder of the workflow, as that's what's presented in the poster. Day 2 will be our TrueCover whole genome sequencing library prep. First, we perform DNA fragmentation using Covaris' Adaptive Focused Acoustic Technology, or AFA. The workflow then moves through end repair and A-tailing, adapter ligation, and magnetic bead cleanup steps that are highly optimized for maximum recovery of DNA. We finish with amplification, another bead cleanup, library quantification, pooling, and then you're ready for sequencing. The key differentiators between both of these workflows is the use of AFA technology. In extraction, we are able to use AFA in order to remove paraffin without the use of toxic chemicals like xylene, making this workflow safer for manual operators and easier on automated systems. At the end of the extraction workflow, AFA provides unbiased fragmenting, which means we avoid the coverage biases you typically see with enzymatic fragmentation methods. Both of these components are critical for the enhanced performance of these kits as compared to other suppliers. And another important highlight that I just wanted to bring up here, especially for clinical and high throughput labs, is the role that automation can play in your FFPE extraction and library prep. Our kits have pre-built automation solutions that can work with industry standard equipment, and our automation team at Covaris is available to help build custom solutions. TrueExtract Smart, our automated FFP extraction kit, was developed via partnership with Hamilton, and it's already been celebrated and presented at leading forums like SLAS, demonstrating higher performance, yield, and purity than many manual kits. In addition, TrueCover is currently being automated and will be available as an automated library prep kit starting in 2026. Critically, our automated TrueCover workflow is a single vessel workflow, which maximizes yield by eliminating transfer steps where you typically lose a lot of your sample. We designed this automation with the platforms you already have in your labs in mind, like the Hamilton Star and Agilent Bravo systems. In the poster I'm presenting today, we put this full workflow to the test. This experiment was designed to rigorously demonstrate the improvements of our workflow as compared to other suppliers. The design of this experiment showcases two key questions. First, how does each component of our workflow perform individually compared to competitors? Second, how does the workflow perform end to end? We compared both of the workflows with competitor kits, creating 4 distinct solutions: the full Covaris solution highlighted in blue, TrueExtract with competitor library prep, competitor extraction with TrueCover, and the full other supplier workflow. The colors that you see here will be referenced through the rest of the presentation, so keep an eye on the blue and orange for full workflow comparisons. For samples, we used 4 very well-characterized FFPE cell lines from the Genome in a Bottle Consortium, HG002 through HG005. These were a part of the Personal Genome Project, and they've been extensively analyzed, so we have comprehensive resources to benchmark our results. All libraries went through the same sequencing and bioinformatic analysis pipelines. This design helps us isolate performance at each step while evaluating complete workflows, giving us the comprehensive data we need to validate our solution. So let's start discussing the data. We'll start with extraction, as this is the foundation for everything downstream. Using our 4 FFPE cell line samples, we perform parallel extractions with the TrueExtract Smart on the Sonication Star versus a manual kit from supplier Alpha. The results here speak for themselves. The TrueExtract delivers a 300% increase in DNA yield compared to the competitor. This yield increase maximizes recovery from limited input material, which is really critical when you're working with precious clinical samples. In practical terms, this means you can meet whole genome sequencing input requirements of 100 to 200 nanograms with significantly less tissue than you would need with a supplier kit. We're talking about only needing 1/3 of the tissue compared to competitor methods, which can be a huge advantage for clinical labs. This significantly de-risks your downstream workflow, and you can count on having extra input material for reruns if necessary. But it's not just about quantity, it's also about quality. When we look at our DNA purity, we see that TrueExtract consistently achieves optimal 260-280 ratios, while other suppliers fall short. This optimal purity ensures downstream reliability in sequencing and analysis, which translates to better efficiency and consistency overall. Together, high yield and high purity mean fewer sample failures, fewer re-extractions, and fewer sequencing reruns. This data shows our extraction provides exceptional input, and we'll see how that contributes to a library performance later. Looking at library yield, we continue to see a clear pattern. We used 100 nanograms of extracted DNA as input for this library prep. Then we amplified with 8 PCR cycles and quantified consistently across all methods. When you use TrueCover library prep, shown again in the workflows in blue and yellow, you consistently see the highest library yields. TrueCover consistently delivers 2 times higher library conversion than supplier A, regardless of which extraction method was used previously. This means TrueCover maximizes the final amount from the DNA input, providing a critical data recovery advantage for our kits. And when we move from library analysis to data integrity and quality control, we can look into data efficiency. The graph on the left here shows the total data loss as we move through the bioinformatic pipeline. We start with 100% of our reads at the beginning, and as we apply quality filters, remove unmapped reads, and remove our duplicates, we continue to lose data at each step. This is very standard, but it's important to note here that the key is retaining as much high-quality usable data as possible at the end. The TrueExtract plus TrueCover workflow in blue maintains around 78% usable data, and it clearly outperforms all other combinations. Now, duplication rates around 20% are fairly common, so this might seem acceptable, but in terms of mapping rate, you really see the difference with TrueCover here. Mapping rate measures how many reads successfully align to the reference genome. TrueCover achieves higher mapping rates above 98%, statistically higher than supplier A. Higher mapping rate means more of your sequencing investment is actually going into your coverage of the genome. Fragmented FFPE DNA usually leads to poor mapping rates, but here we see that the TrueCover advantage provides that enhancement. TrueExtract and TrueCover together really maximize the amount of quality data available for downstream analysis. So whatever type of analysis you're doing on your FFPE DNA, it's great that you can get the most out of your sample prep. Finally, as we move into more advanced bioinformatic analysis, we can compare performance on real-world diagnostic tools, variant calling concordance. This is kind of the key point that brings everything we discussed previously together. Variant calling identifies genetic differences from a reference genome in two different categories, SNPs and indels. The F1 score shown here balances sensitivity, how many true variants you detect, with precision, aka how many calls are actually correct. A perfect F1 score is 1. Anything below means you're either missing real variants or calling some false positives. In cancer genomics, this is a really big difference. We're often looking for low-frequency variants in heterogeneous tumor samples, which means variants might only be present in a small fraction of cells. Missing a clinically actionable mutation means a patient might not get the targeted therapy they need. Calling false positives wastes time, resources, and can really often lead to incorrect treatment decisions. In this panel, we focused on OncoKB's Tier 1A genes, which are the 58 genes with FDA-approved targeted therapies. These directly determine treatment options for cancer patients when they're correctly identified and can lead to a lot of downstream issues. The results are pretty striking here. The full TrueExtract plus TrueCover workflow, again in blue, delivers the highest F1 scores for both SNPs and indel calling. Once again, the stepwise improvement shows that TrueExtract significantly improves over supplier alpha and that TrueCover improves it further. The synergistic benefit we see here was illustrated in holistic variant calling workflows and on more challenging types like indels longer than 16 base pairs. We're maximizing true variant detection while minimizing false positives, which can cause unnecessary interventions. It's really difficult to overstate the impact that precise, accurate variant calling can have on cancer patient diagnosis. The numbers shown here translate directly to the number of mutations correctly identified by each workflow, and the higher proportion correctly identified by the Covaris TrueExtract plus TrueCover workflow means that 2 to 5% of patients would be receiving a more accurate diagnosis than a supplier workflow and could access better treatment days to weeks earlier. At the beginning, I outlined the critical challenges facing FFPE-based cancer genomics workflows. Now, let me show you exactly how our solution addresses each one. First, we see signal loss at extraction. Those precious low-frequency variant molecules are permanently lost. Our solution, TrueExtract, maximizes molecular recovery, delivering 3 times higher DNA yield. You're capturing more of those rare variants right from the start. Second, contaminants and inhibition skew quantification and reduce library conversion efficiency. Our solution is that TrueExtract delivers statistically superior purity, ensuring optimal DNA quality and translating to efficient downstream processing. Third, we have issues with false positives and missed indels. Low-fidelity prep creates artifactual variants. Our solution, the complete workflow, delivers the highest F1 scores, optimizing precision and recall for both SNPs and complex, hard-to-detect indels. And fourth, we see irreversible sample loss when sequencing fails on low-yield libraries. Our solution is that TrueCover creates an operational safety net for any user, The 2 times higher DNA yield we see here creates critical surplus material for repooling and recovery. And finally, the overarching need for a validated, automated workflow that de-risks every step. Our solution, the highest documented success rate in our study, delivered with a 2-day FFPE workflow from sample to sequencing ready libraries. This is how we're transforming cancer genomics, addressing every critical challenge with proven, validated solutions to better help patients, providers, and everyone who can benefit from a better FFPE solution. Thank you so much for your time today. I hope this has demonstrated to you how the TruExtract and TrueCover workflow addresses the real challenges you face in FFPE cancer genomics. With TrueCover automation launching in 2026 on platforms like Hamilton Star and Agilent Bravo, this will soon be a fully automated solution that works with your existing infrastructure. I'm happy to take any questions you have.
Thanks, Bella. That was so interesting. It really sounds like a step forward for achieving high quality data in genomics. I do have a few questions off the back of that, if that's okay. So the first one is, can you explain why FFPE presents consistent challenges for whole genome sequencing and what motivated your team to take a deeper comparative look at extraction and library prep workflows?
Yeah, awesome. This is a really good question. So FFPE tissues are really essential for a range of clinical applications. But what we were focusing on here was how they're like directly critical for cancer genomics research. Um, and we also see that when you're looking at whole genome sequencing, which is what we chose to focus on, your issues are amplified. So when you are working with whole genome sequencing, you need comprehensive even coverage across the entire genome. So any extraction inefficiencies or library prep biases or any issues you might have just become apparent. You can't really rely on super high depth sequencing to compensate. You really need good reads across, all 3 billion base pairs in the human genome. So what motivated our analysis was just we kept seeing inconsistent results from other competitors in the field. Different extraction and library prep methods really claim to handle FFPE challenges, but there wasn't clear data on how they perform against each other in a controlled setting. And we wanted to rigorously compare our kits with competitor kits using the same reference samples, the same sequencing depth, and standardized bioinformatic pipelines. And we hope that this provides clear quantitative metrics that can help researchers and clinicians make informed decisions about their whole genome sequencing workflows from FFPE.
Amazing, thank you.
Mhm.
A second question that came to mind was your study highlights substantial improvements in usable read retention, insert size consistency, and variant calling accuracy. What
Mhm.
aspects of the Covaris workflow contribute most to the performance gains, would you say?
Yeah, absolutely. So a lot of this is really attributed to adaptive focused acoustics or that AFA technology we talked about a little bit. This can really be attributed to that like unbiased fragmentation, which is a big differentiator in the Covaris workflow versus competitor kits. So AFA provides like very truly random sequence independent fragmentation, whereas you get to enzymatic shearing, it can introduce a lot of biases, preferentially breaking at AT-rich regions, and it can create non-random distributions where you're losing a lot of those areas of the genome that are typically difficult to sequence and do variant calling in. And what we see from AFA is that we get much more consistent insert size because of the precision here, and we also lose a lot of the GC bias. So you're essentially removing fragmentation bias, which is a major source of technical variability from an already very challenging sample type, which maximizes the amount of genomic information extractable from these kinds of tissues.
Yeah, sure, makes sense. Thank you. And then a last question that I had was, so for labs that routinely work with variable or low quality FFPE blocks, what practical steps can they take to improve whole genome sequencing outcomes, and how does this workflow support those efforts?
Absolutely, yeah. So I think that for labs working with FFPE samples, there's a lot of places to implement improvements. And I think optimizing extraction can matter a lot more than people realize. Balancing that like really aggressive deparaffinization and decrosslinking without damaging the DNA can be really difficult. And TruExtract was designed very specifically with that balance in mind. So that's why we see such great results here. You can get more DNA yield and DNA quality compared to competitors, even from the same starting blocks. So really not neglecting that extraction can be big. And it's also important when you're doing your library prep that you focus on accommodating the short damage fragments that you're going to get from FFPE DNA. So even when you look at the TrueCover whole genome sequencing kit, we have protocols for non-FPE DNA and FFPE DNA, and we choose to use a shorter, more optimal fragment size for that damaged DNA, which really goes a long way in getting consistent reads. When you get the sub 200 base pair fragment size that we really recommend based on our extensive testing, you're able to get much more consistency. And it's also helpful to use a standard bioinformatics pipeline so you can benchmark against competitors. So we used a lot of standard pipelines. There's also a lot of really awesome additional tools that researchers are working on specifically for FFPE samples, a lot of which use machine learning and deep learning, which we didn't use here, but can be a huge asset to labs. So overall, I think it's important to really focus on consistency and what gives you the best results overall.
Amazing. Thank you. Thank you so much for joining us today. That was super, super interesting.
Awesome. Thank you so much for your time. I really appreciate the opportunity.
Thanks for watching this Science Spotlight. To learn more about the workflows Bella discussed, check out the links in the description. And if you'd like to see more Science Spotlight content, don't forget to like and subscribe to catch all our latest releases.